here, candy. And here, I'll give you a candy for your question also, even though it's... All right, so we were talking about infinite series. We want to get through this chapter as quickly as possible. We're sort of 3/4 of the way through if we are talking about the essential mathematics as opposed to the examples. And so the next topic is really just a definition. It's the definition of a Dirichlet series and a zeta function. And these are things that you should, just sort of know about. A Dirichlet series and does anybody know what language this name is from? Is it French? I've been assuming that, but I really don't know. So this is something like this. So this is a very strange kind of a series. It's not a power series. Z is in the exponent of n. And an example is the Riemann zeta function. Zeta of z, which is the sum n equals 1 to infinity of n to the minus z. So you just said all the cn is equal to 1, and that's the Riemann zeta function. I once was working something out, and a friend of mine said, "What's lightning?" And I said, that's zeta. Anyway, this converges for real z greater than 1. And Euler showed various things about this Riemann zeta function, namely that it's a product over all primes of 1 over 1 minus prime to the minus z. I mean, that's pretty remarkable. What I would do with it, I don't know, but it's a remarkable formula. Some specific values, zeta of 2 is pi squared over 6. Zeta of 4 is pi to the 4 over 90. And these days you can just Google zeta parenthesis 4 close parenthesis, and out comes pi 4 over 90. So, yes?
Dirichlet is German.
German! Okay, so what am I going to say? Dirichlet, I guess.
But he worked for France. He was German, but he did his work for the French government, for the French, according to Wikipedia.
All right. We'll call this D. Anyway, this occurs in the Planck distribution. So the energy density at inverse temperature beta, frequency nu, volume v, it's 8 pi hv over c cubed nu cubed q nu over e to the beta h nu minus 1. Should I continue with this example, or have you guys seen black body radiation in your stat mech or? Yes, you're seeing? So
yes, we've seen it.
You've seen it. All right, well, I'll just leave it there then. In the calculation, what one does, let me just put the mathematical part in there. You translate this to, you change variables and you get something like this, x cubed over e to the x minus 1 dx from 0 to infinity. So that's an integral that occurs here. And then what you do is you multiply by e to the minus x top and bottom, and that turns out to be 0 to infinity x cubed e to the minus x 1 minus e to the minus x dx. And now you use the infinite sum formula for 1 over 1 minus epsilon is the sum of epsilon to the n. And so this thing is integral x cubed e to the minus x e to the minus nx, and that's it, dx, sum, n equals 0 to infinity. And then each of these guys, each of these integrals gives, you then wind up with a sum 1 over n plus 1 to the 4th power from this integral. I'm leaving out a 3 factorial actually. So maybe I'll put a 6 here. And this, of course, being a sum from 0 to infinity, if you shift and make it a sum from 1 to infinity, then it's the zeta function. So this is 6, the zeta of 4. 4 being because of that exponent. All right, so that's the end of that example. Bernoulli numbers, we can skip the Lurch transcendent. The Bernoulli numbers are defined this way, x over e to the x minus 1. We write it as a sum of, well, obviously it's the sum x to the n over n factorial, dn, dx to the n of x e to the x minus 1. N equals 0 to infinity. So this is just writing a Taylor series for, yeah?
I have a question. I had the question a long time ago.
Thank you for your patience.
On that equation for the Riemann zeta function, I understand the part with the sum, but you have some part with the product. I'm wondering what P is. Because
P is a prime.
and you go to infinitely many
1,
times.
3, 5, 7, 11, I guess.
And you like it is product to the infinity.
Oh yeah. All the primes, yeah. Yeah, some of these mathematicians there in the 19th century, they really thought about pretty strange things. And the interplay with number theory and analysis is something that's always, I find fascinating, but I've never been fascinated enough to actually look at it carefully. I just would basically say wow and then turn the page. Anyway, this is sum n equals 0 to infinity, the nth Bernoulli number x to the n over n factorial. It turns out beta 0 is 1, beta 1 is minus a half, but all the other odd ones vanish, and there's a formula for the even ones, and beta 2n, for example, is minus 1 to the n minus 1, 2n factorial over 2 pi to the 2n zeta of 2n. And this is, of course, n greater than 0. I say n greater than 0, so it may be, well, these are only for integers, so it's just positive integers. All right, I think I'll leave that subject because we want to get on to complex variable theory. Suppose we have a series that looks like this. Sn is some sum up to n, k equals 0, a sub k over, let us say, x to the k. This is a typical form of an asymptotic series. And what often happens is this: if we define Rn to be the remainder, in other words, it somehow is approaching some function f of x, and we say the error is R sub n, or the remainder. Obviously, if we have a formula like this, we don't expect it to do very well at x equals 0. This is not what we're looking, this is a formula for large values of x. And so this is an asymptotic series if we have something like this. Limit x going to infinity, x to the n, or n of x equals 0. So that's saying that it's really a pretty good series, because the last one would, the remainder, in other words, would fall off as 1 over x to the n plus 1, say. That's the idea. And you remember when I was talking about Merman's and Ramanujan's marvelous formulas for n factorial, and I got kind of confused because when I looked at the picture, if I can sort of redraw the picture, these are asymptotic series. So if you look at figure 4.1, then what's plotted here, n is like 0, 10, 100. We're talking n factorial. And what's plotted on the y-axis here is 10 to the 8th times the error, which would be r sub n, minus n factorial divided by n factorial. So this is the relative error, but magnified by 100 billion. So we're being very critical here. And if you plot Stirling's formula, it's just off the page. And here is 0 minus 5. And Merman's, let's see, Ramanujan's does this. Merman's first formula does that, first approximation, but his second approximation, or is it his third? It must be his second approximation. Yeah. His second approximation is that. So it's for small n, it's not so good. That's because there are terms 1 over n there. On the other hand, what this is saying is that his approximation, first of all, these are all asymptotic series, and secondly, his approximation is better. Well, it's better for smaller n, but of course we're talking 10 factorial, so it's 10. I mean, it's not 10 to the minus 3 or anything, it's 10 or 20 and so forth. So that's why that was sort of, all right, I think I'm going to basically skip the electrostatic problems. Those of you interested in biophysics might want to look at that. Those examples, and the examples are also, they also illustrate some electrodynamics that you probably learned 3 or 4 years ago, and so this will be kind of a review. Some story they were saying that nothing pleases a professor more than to hear a statement that he already knew. All right, I'll leave that aside. All right, now here's a definition, and this definition is important. All right. So first of all, we've got a function f of a variable z. And normally when I write z, I mean a complex number. So we're talking z is, for example, real number x plus I times real number y. I squared, of course. All right. Now, we say this thing is differentiable. Differentiable at z. If we can define this f prime of z as a limit, z prime goes to z, f of z prime minus f of z over z prime minus z. Okay, now this is obviously the same definition in one sense as if you were talking about just an ordinary real function. So when you first learned calculus as freshmen in college or high school seniors or something, you learned that if all these z's were real numbers, this is the definition of a derivative for a real value function of a real variable. Okay. But the subtlety here is that z is complex now. And so there are many ways for z prime to go to z. Just as there are many ways for a lawyer to write a law or a contract, or to interpret a law or a contract. So you might say, well, this is the limit, and so here's the point, z. You might say it's the limit as we approach from numbers that differ from z by having a bigger real part, or a smaller real part, or they come down from the imaginary, from having a larger imaginary part, or a smaller imaginary part. Or you can say that they spiral in some funny way. The point is that if all of these limits are the same, then the function's differentiable. So it's differentiable at z if the limit exists and is the same for all paths, let us say, z prime to z. So that's the idea. So the point is, the new wrinkle is that in the complex plane, z prime can approach z in all kinds of crazy ways, and if you get the same limit no matter how you approach, then the thing is differentiable. So that's the idea. That's differentiable. There's another term, analytic. So we say f of z is analytic at z0 if it's differentiable at z0 and in some disk around z0. Okay, so that's the idea for analytic. It has to be differentiable not only at one point, but in a small, tiny region around that point. Example, f of z equals z to the n, polynomials, or just a monomial. This is differentiable, and the way we see that is f prime of, let us say, z plus dz. Well, f prime, all right, let me read. F of z prime minus f of z, f of, let us say, z plus dz minus f of z. So dz, which is distinguished from dizzy, dz is just some small complex number. So this is z plus dz to the n minus z to the n. And for small enough dz, just expanding this using the binomial theorem or whatever, it's n z to the n minus 1 dz. So that's approximately true. And now we take the ratio f of z prime, or z plus dz, minus f of z over dz. Well, this is nz to the n minus 1 dz over dz, and this is nz to the n minus 1. And so it's exactly what you'd think, because if this were a function of a real variable, you'd say the derivative was nx to the n minus 1. So this is but now we see that for this particular case, there's no problem dividing through. Okay. And what's generally true, this is sort of a rule of thumb as opposed to something that you could say in the math department, But as a rule of thumb, if the function is a function of z, then it's analytic at z unless there's something crazy happening at z. So, and of course crazy things do happen. And in other words, there might be an ambiguity of a definition. So with square root of z, you'd say, well, there are two square roots, plus and minus. So something funny is going on in square root, so it's not obviously analytic. Log of z, there are some ambiguities there. 1 over z, well, that's a little sick at 0. So basically though, if the thing is not ambiguous and it's not infinite and there's nothing funny happening, it's normally analytic at z, wherever you are. Another definition. Suppose a function that's analytic everywhere and such a function is said to be entire. So entire means that it's just analytic. And polynomials are entire. All right. So again, rule of thumb, when is a function not analytic? Well, suppose it's just a function of x and y. And suppose we had f of x and y is x squared plus y squared. So for any point in the complex plane, and we can think of the complex plane as being a two-dimensional plane, x, y, and we can say there's a point z there that is x plus I, y. Well, suppose that this is your value, and this, of course, is z bar, z complex conjugate. I like bar better because it's one line, where star is 3 lines. They're shorter, but it's still, you have to hit the 4 3 times. And the idea is, let's suppose we define the derivative in the x direction. Well, then we have f of 1 plus epsilon 0 minus f of 1, 0 over epsilon. And now what is that? That's 1 plus epsilon squared minus 1 over epsilon. And so this is 2 epsilon over epsilon, and so this is 2. So this is coming in on the real axis, limit on the real axis. And the point here is 1, 0. So we're computing the thing at 1, 0. Now suppose we do it from the imaginary point of view. Then it would be 1 epsilon minus f of 1, 0 over epsilon. Over now, not over epsilon, it's over I epsilon. Because the point in the complex plane is IY. dz is IY. And so this is 1 plus epsilon squared minus 1 over I epsilon. And the answer is minus I epsilon, which is 0. And you get a different answer even if you hadn't put an I here. You would still obviously have gotten 0. Okay? So that's an example, and that illustrates the fact that if you can't write the thing as a function of z, it's typically not analytic. You might want to check, but it's typically not analytic. Okay. So that's 10%, I would say, of complex variable theory is just understanding this definition. All right. Another 10% is Cauchy's integral theorem, and this is a simple integral theorem. It's basically that if you have an analytic function and you integrate it around a closed curve, you get 0. So let's see this in a suitable context. So first of all, let's consider a function that is differentiable at z0, in fact is analytic at z0. So it's f prime of z0, z minus z0 plus higher order terms, and this being a physics department, we'll just keep those two. And, okay, now, here is something that you just got to get straight. It's very simple. You can say z is z0 plus epsilon e to the I theta. So in other words, I'm talking about a little circle. Here's z0. I'm going to go out epsilon in the real direction, and then I'm going to go around in a circle. So that's going to be the path of integration. A simple circle. Small circle. And so theta goes from 0 to 2 pi. And when we have an integral in the complex plane that starts at some point and comes back to the same point, LaTeX has a symbol for it. It's called \ON. And so what is this? F of z dz. Well, this is an integral, 0 to 2 pi d theta, because all we're changing here is theta. Theta is this angle. And what we've got then is z minus, it's f of z0 plus f prime of z0 times z minus z0. So this is, in as much as this is a very tiny circle, this is a good approximation. And we have dz. Well, what is dz here? dz, since z is this, dz is epsilon I e to the I theta d theta. And that's, you know, obviously true. If z is this, then dz in the sense of d theta is just I epsilon e to the I theta d theta. So what we got here then is I epsilon e to the I theta d theta. So we want to do this integral, and it splits up into two parts, both of which are 0. So we have integral 0 to...
You have two d thetas in the same integral.
What's that?
You have two d thetas in the same integral. I'm just
Yeah,
commenting.
no, you're absolutely right. Thank you. All right, let's get rid of this. Do you want two candies or just one?
That's okay. I don't need any candy.
All right, I need a drink of water.
Okay.
Any questions?
I was trying to create a general accessible as well. Yeah, it's not easy to do this.
Okay, so let's see what this is. There are two terms, and in fact, in the first term, we can just factor out f of z0. And so this is I epsilon e to the I theta d theta. Well, this integral is obviously 0. In fact, it's one advantage of having done the Fourier series chapter first is that we're familiar with integrals like this. You just, this integral is 1 over I, and then you evaluate e to the I theta at 2 pi and 0, and they're the same. So the difference is 0. The second term is this one, f prime of z0, integral 0 to 2 pi. And now, let's remember what this is. This is z minus z0, so this is epsilon e to the I theta. And so this thing is epsilon e to the I theta, I epsilon e to the I theta d theta. Well, this is also 0. So this one's 0. Because it's the integral of e to the I theta, this is integral e to the 2I theta, so this is 0. Because it's an integral from 0 to 2 pi. Okay, so what we've got then is that the integral f of z dz around z0 size epsilon equals 0. So we proved, but we the result though is quite general because I've proven this for an arbitrary analytic function. This is every analytic function. Okay, now we're going to see what happens. Just to give you the feel of things. Let's repeat the thing, but now have z0 the center of a cube, a square. Sorry. And
Professor K, quick question. Just about the definition of an analytic function. Is every analytic function's derivative also analytic? Like, can you keep taking derivatives and trying to get analytic functions out?
yeah,
Okay.
good observation, but you make me nervous when you get too far ahead of me.
Well, I was just thinking about
No,
whether
no, no,
or
I'm
not
not
the Taylor
being
expansion
critical,
will
I'm just-
converge.
You wanted candy.
No, it's okay.
The derivatives might not always stay entire, though. They might be, like, you might take some derivatives and then you started with a function that was entire, and the derivatives ended up not being entire.
Okay.
All right. Well, can you, I think we want this, yeah, good, okay. All right, let's do the square. So this one we'll call dz1. So dz, size epsilon. So dz1 is just epsilon. That's this one. dz2 is going to be I epsilon. dz3 is minus epsilon. And dz4 is a minus I epsilon because we're going down. And now we're going to approximate the functions as being at the center of each of these. So we're going to say then that our integral f of z dz is the sum f of zn dzn n equals 1 to 4. So this one, that one, that one, that one. And this is then a sum n equals 1 to 4 f of z0, which is just f the center, plus zn minus z0 f prime of z0 dzn. And now we just have to add these things up. Obviously, it's going to come into a sum of two things. It's going to be f of z0 times I1 plus f prime of z0 times I2. So in other words, this one is just the sum of the dz's, and so in other words, this is f of z0 times dz1 plus dz4 plus f prime of z0, and then this would be z1 minus z0 dz1 plus plus z4. Z4 minus Z0 dz. So those are the two terms, and now just work them out. Well, the sum of these guys is obviously 0 because they go from here to here to here to here and then back to here. So the sum of all these is then 0. But so also is the sum of these, although it's not so obvious. So the sum of them is, the first one is, let's see, did I say what the z minus z0 is on? Maybe I should say what the z minus z0 is. The first one is z1 minus z0. So this is minus I epsilon over 2. And dz1 is epsilon. The next one is just epsilon over 2, because that's z2 minus z0. And now the dz2 is I epsilon. The next one is I epsilon over 2, but now it's minus epsilon because dz is going that way. And the last one is minus epsilon over 2 because the dz, I'm sorry, the delta z, z4 minus z0 is minus epsilon over 2. dz is minus I epsilon. Okay, so I've done these without looking at the page. Let's make sure that it's right. Epsilon squared divided by 2 times minus I plus I minus I plus I. Well, that's equal to 0. Okay. So this shows then, for arbitrary analytic function, the integral around a small square is 0. And of course, being able to write f prime and s prime and use the approximation, I'm assuming that we're within a region of analyticity for this whole calculation. Okay. All right, the next thing is to use the trick that you've seen in college calculus classes when there's a discussion of surface integrals or Stokes' theorem or things like that. And the idea here is we're going to consider the integral around a big square. So here's our big square of side L. And so this is the integral that we're going to be talking about. And we're imagining that this is inside a region of analyticity. And we have some function f of z that's analytic in a region that completely encloses this square. And now we're going to divide this thing into small squares of size epsilon. And so what we're going to have is we're going to have L over epsilon squares, this segments this way, L over epsilon segments that way. And so the total number of squares is L squared over epsilon tiny squares. And we imagine, I'm going to draw this square big though, so because if I draw it really small, I won't be able to draw well and you won't be able to see it. So here's our little square. And we're doing this integral. But then we're also doing this integral. And you see that the two integrals on this edge cancel. Okay, heads up. I'm just trying to make sure that everybody sees this. So this one cancels. And then when we do this square up here, this one cancels. And then we do this square, and then these guys cancel. Anyway, what happens is all of the integrals just cancel identically, and we're left with simply the integral around the total square. Okay. Now I recall that since I wasn't carefully following my notes, I forgot to say something. What I forgot to say is that this integral around the tiny square is identically 0 to order epsilon squared. And so the error is order epsilon cubed. So what we know then is that all of these individual squares, what can they amount to? All they can amount to is something of order epsilon cubed times L squared over epsilon squared, which is epsilon L squared, and that goes to 0 as epsilon goes to 0. So what we've proven then is that the sum of all these integrals around all these tiny squares, the sum of all those, each one we know is 0, but if we weren't absolutely certain it was 0, I mean, what we've proven here in our physics way is that it's of order epsilon cubed. We've shown that the coefficient of epsilon squared is 0 and epsilon is coefficient of epsilon is 0. So this can be at most epsilon cubed. There are L squared over epsilon squared over, so the total value of the sum of all of these things, worst case, it's epsilon, it goes to 0. On the other hand, just analytically, because all the interior integrations along all these little segments of size epsilon cancel, the sum of all these integrals around all these tiny squares is equal to, so this sum is equal to, on the one hand, is equal to epsilon L squared, and on the other hand, it's the integral dz f of z around the square of size L, because the only thing that's left is the integral around the outer edges. Those are the only edges that didn't cancel. And so what we've now proven is the integral around the square that's big of f of z dz is 0 for arbitrary analytic functions, as long as the thing is analytic around the square. All right, so that's I'm looking for this other piece that I cracked in two. That was therefore fractional. Here it is. All right, so that's yet another example of Cauchy's integral theorem. All right. Now the next. So any questions? So far we've shown that integral around a tiny circle 0, integral around a tiny square 0, integral around a big square 0. Now we need to go to basically an arbitrary case. So let's consider a contour integral. So let's suppose we have some region of analyticity. And we have a point here, z1, and another point here, z2. And we go from one to the other along some contour, C. And, all right, wait a minute, I think I just skipped something. Yeah, I just skipped something. So let me find some blackboard space. All right, here's a region of analyticity. And suppose now we're going from Z1 to Z2, straight line. And so we're considering Z1, Z2, f of z, dz, and it's on this line, which I'll call S straight. Okay. But now, look what we can do. You see, we can add a little square here, like that. So now the integration is all the way along there, but we add to that this little square integral. And what happens is the part that's integrated twice but in opposite directions cancels. So the actual integration after you've included the square, it looks like this. So in other words, it looks like that. And now, obviously, you can do this again. And you can decide that, well, we're going to put a little square here, and so now it looks like that, and so forth. And what's made Cauchy's integral theorem more understandable is the advent of personal computers with screens that until recently had pixels, and you could see pixels. Unfortunately, Apple's made such progress that the latest machines now are so-called retina displays. You can't see the pixels anymore, and so it's going to be much harder to teach complex variable theory. But if you imagine this whole square is just a lot of pixels, and each pixel is a little square, and so you can arbitrarily deform this thing until finally you've got something that on a retina screen would just look like a curve. But on something of less resolution, you'd see it was actually a bunch of squares. Or actually, well, all right, never mind. I'm not going to try to do the engineering quite so accurately. But the point is that we've gone from the straight line integral to the curved integral just by adding a bunch of little pixels, square pixels. And that's changed the contour. It first changed it to that, and then it changed it to that, and then after a while it's changed it to this. So the point is that the integral from z1 to z2 of a function that's analytic in a certain region, it depends upon z1 and z2, but it doesn't depend upon the path. You can deform the path. You can make it like that as long as you stay within the domain of analyticity. And so that means then that these two paths give you the same integral. So if we call that c and this c prime, we can say the integral z1 to z2 on c of f of z dz is the same thing as the integral z1 to z2 f of z dz on the contour c prime. Again, if we're in that same domain of analyticity. Okay. Now, suppose we change the contour in a sort of discrete way by, instead of going from z1 to z2 on c prime, we go from z2 to z1 on c prime. Well then, this thing, the integral from z2 to z1 along c prime, or maybe I should call it minus c prime because it's backwards. So this would be of f of z dz, it would be a sum of all these infinitesimal elements dzi, f of zi, and the f's would be the same whether we're going from here to there or from there to there. It would just be that the order would be different. But each of the dz's would be opposite. There would be the dz going that way, and then the dz going that way. And so this integral from z2 to z1 is minus the integral z1 to z2 of f of z dz. Okay. So now we come back to this arbitrary to this region here of analyticity, when we go from Z1 to Z2, say, we go that way along C, and now, instead of going that way along C prime, we go this way along C prime. Maybe we call it minus C prime. Well, the sum of the two integrals is just an integral of f of z dz from Z1 to Z1 again, out along C, this is not C prime, out along C, and then back on minus C prime. So we go along here to Z2, and then we come back that way. And what's the answer? Well, the thing is that Z1 to Z2 on C of f of z dz plus the integral from Z2 to Z1 on minus C prime of f of z dz. And this is the integral from Z1 to Z2 on C of f of z dz minus the integral from Z1 to Z2 on C prime f of z dz. So in other words, on this one we're going backwards. On this one we're going backwards. On this one we're going forwards. And the backwards is minus the forwards. On the other hand, we just showed back over here that the integral on C from Z1 to Z2 is the same as the integral on C prime from Z1 to Z2. So the difference of these two is 0. Okay, so now we've actually proven Cauchy's integral theorem, namely that the integral f of z dz is 0 as long as we're inside a region of analyticity. And there's one more subtlety. These regions of analyticity, I've always said, were just very simple regions. They were whatever was inside my irregular ellipse, say. I mean, I just draw some cold thing, I mean everything inside. So there is a subtlety here, and the subtlety is kind of interesting because it has a topological flavor to it. And the idea here is that, see, the intrinsic thing was that we could, maybe turn the thing a little bit. You see, what we did here was we added pixels and we deformed the contour from here to here, and we said the two integrals are the same. Well, but as we do the deformation, we have to stay within the region of analyticity. Otherwise, it doesn't work. So that means that the Cauchy's integral theorem holds as long as you can take this contour and move it from here to there, staying within the region of analyticity. And that's related to something called simply connected. And to give you a picture of simply connected, let me just say, American cheese is simply connected. Swiss cheese is not simply connected, okay? A dime is simply connected. A washer is not simply connected. I'm assuming a washer looks like this. Is that right? Is that a washer? I grew up in New York City, and anything having to do with anything practical was just totally outside my youthful experience, except dodging cars from crossing streets. By the way, the reason the baseball team was called the Dodgers is that in Brooklyn, the city or some private organization put trolley cars in. And these trolley cars were very quiet because they were electric. And I imagine the first few weeks, people were being killed by the trolley cars. And the trolley car would come along, and this guy who might be half drunk would be walking across the street and wouldn't hear the trolley car coming. And of course, then he didn't hear the trolley car going either. But anyway, and so after a while, the people learned that they had to watch for the trolley cars and they had to dodge the trolley cars. So they, everybody in Brooklyn thought that they were basically Dodgers, and so they called the team the Brooklyn Dodgers.
That's the real reason?
Yeah, yeah, no, really. And by the way, while we're talking about baseball, you know, people often quote Yogi Berra because he had these sayings which were both, they seemed silly, but had some meaning, and so people like to quote them. One of them was, if you come to a fork, take it. And of course, with a fork in a road, you don't know whether to go left and right. What he was actually talking about was how to get to his house. And he had such a large property that when you drove to his house, the road would fork, but both of the forks led to the house, so you could just take the fork and you'd get to the house. That's the actual explanation of that. I read his obituary before he died. Okay. So let me say something. This is the term simply connected. A region is simply connected if you take 2 points in the region and say you connect them with a curve, or let us say you have take any closed curve in the simply connected region. You can shrink it to a point while staying in the region. Okay. So you can take this thing, you make it like that, and then like that, and then sort of like that, and then you've gone all the way over here, and now it just has no area at all between it, and then you can suck this one up to there, and it's become a point. So that's the idea of simply connected. And so you see with Swiss cheese, you've got a hole here, and so you've got some closed curve, and you shrink it, and then you get in the hole, and so it's not simply connected. Let's see, I had another example of this. Yeah, a sphere, the surface of the sphere, just the surface of the sphere. It is simply connected because you can take any curve on the surface of the sphere and shrink it to a point. But now if you imagine this is actually a bagel, well then you can have a curve here and you can shrink it to a point. But if you have one like that, then you can't shrink it. And if you have one that goes this way and then around the other side of the bagel, can't shrink that to a point. And so bagels are not simply connected. On the other hand, thinking of the surface of the bagel is not simply connected. On the other hand, if you're hungry, you're interested in the volume of the bagel, not the surface of the bagel. And so let's think. The volume of the bagel is that. No, that's not simply connected either, because you can have a curve that just goes through the center of the bagel. It's not. But for a sphere, again, the sphere as thought of as three-dimensional, that is simply connected. Okay. All right. So let's see. There was yet one more proof of. Well, I think we've sort of done that enough. All right, so in particular, if we have any polynomial Polynomials are entire. The integral of any polynomial around any closed loop in the complex plane is 0, and we don't have to worry about what the region is. On the other hand, suppose we have a function like this, 1 over z minus z0. Well, now, you can work this out, and you can see that this is analytic, except where it goes bad, namely when z is equal to z0, it's infinite. So basically, this is infinite, not infinite, it's analytic, except at z0. So the region of analyticity is not simply connected. It's the whole complex plane, except for one point. All right, well, let's see if we can do Cauchy's integral formula now, because the definition of analyticity plus Cauchy's integral theorem, that's at least 20% of complex variable theory. We'll get to 30% if we can do Cauchy's integral formula. And it's pretty straightforward. All right, so let's think about it. So let's consider an integral. And we're going to start out again in a physics kind of way by saying that this is a contour of radius epsilon, just a circle around z0. And so this is an integral then. We can say this is f of z0 plus f prime of z0 times z minus z0. And dz, so z minus z0, I'm going to say is epsilon e to the I theta. dz is I epsilon e to the I theta d theta. So it's the same trick as before. And so this is I epsilon e to the I theta d theta. And z minus z0, well, this is epsilon e to the I theta. In other words, we've got this point, z0, we're going out a distance epsilon, and it's going to be epsilon e to the I theta for this little circle. And now, just as we did it before, this is an integral 0 to 2 pi. So this is integral 0 to 2 pi f of z0 plus f prime of z0 epsilon e to the I theta I epsilon e to the I theta d theta, and then epsilon e to the I theta. Okay, now it's like the case that I did over there, the other side of this room, except that I need these parentheses here, and this first term, this integral isn't going to be 0, because you see this integral now, if you cancel the obvious things, this is going to be f of z0 plus f prime of z0 epsilon e to the I theta I d theta. And now this integral, the second one, that's going to be 0. Because it's just e to the I theta from 0 to 2 pi 0. But this one, well, this is very simple. This is just d theta from 0 to 2 pi, that's just 2 pi. And, oh, yeah, I'm sorry. Yeah, right. In other words, this is just f of z0 I d theta, and so this is just 2 pi I f of z0. So that gives us Cauchy's integral formula for this case, namely f of z0 is 1 over 2 pi I, integral around the tiny circle, f of z over z minus z0 dz. Okay, so we've proven it for this special case of a tiny circle. Now we use a trick to do it for a big circle. And this trick is a trick that's used many times in complex variable theory. You can deform your contour, so you might as well use any contour you please. And so now this contour that I'm going to use is a kind of a strange contour. We're going to go in like this. We're going to go backwards around z0, counterclockwise. Back this way, big circle, or ordinary size circle, like that. Now, and imagine that this whole blackboard is a region of analytic. Okay? All right. Now, what we can do is, I'm going to call that contour C prime. So C prime goes up, in, around, over, around, and back like that. That's C prime. And we have f of z as an analytic function. So we know that 0 is 1 over 2 pi I integral C prime f of z over z minus z0 dz. Because we can deform, and where, here I'm thinking of this as the analytic function. This is analytic except at z0, so I can deform the contour, not changing anything, as long as I don't cross z0. And so I take this part and I swing it back, I take this part and I swing it back, and I squeeze it all together at point 0. Okay, so that's 0. Now what we do is we let these two contours approach each other. And so those integrals cancel. And so what we can say is that this is 0, and it's 1 over 2 pi I. Right. It's 1 over 2 pi I times, let me say that the contour C is the contour that's just a big circle. Doesn't really have to be a circle, but a big loop around Z0. So the contour C prime is this big loop, these two guys which cancel, and then this counterclockwise loop of radius epsilon. And the counterclockwise loop of radius epsilon is the clockwise loop with a minus sign. So this is minus the integral, minus 1 over 2 pi I, the integral radius epsilon now, of f of z, z minus z0 dz. So this integral is the one I just did there, the tiny circle. It is minus that. So C prime, the integral on C prime is 0. C prime is C minus the epsilon contour. Yes, minus the epsilon contour, because the C prime contour was backwards. But we know what this is. This is f of z0. And so we arrive at Cauchy's integral theorem. F of z0 is 1 over 2 pi I integral f of z, z minus z0 dz. dz, as long as we stay within a simply connected region of analyticity of the function f. All right, any questions? I think I'm going to stop here. I'll just tell you, have I told you guys the story, Lyndon Johnson's story about the man who applied for a job at a switchyard?
Should we turn that off?
What?
Should we turn it off?
No, leave it on. Be the most interesting part of the lecture. So, Lyndon Johnson had many, many stories, and this story was about some guy who applied for a job as a switchman in a switchyard in someplace in Texas, and he had to, and they gave him a test, and one of the test questions was, if you saw two trains approaching each other on a track, what would you do? And he said, well, I'd call my brother. And the instructor said, well, why would you call your brother? Well, he ain't never seen a train wreck. All right, I'm obviously not gifted as a comedian. I will not try that as a... All right, any